Hello everyone. Just wait for everyone else to join and then we can start. Hi Rohit.
Hello.
Hello. Yeah. Seems today I can hear you clearly. Uh, Saransh said he will be joining, but I don't see him yet. So, mhm. Well, already I'm late by 3 minutes. Let's start. I believe he'll call it. Yeah, I think Saransh is joining in as well. Let's give him 1 minute. Great. Hi Saransh. Can you hear us?
Um, yep.
Okay, great, great. Okay, then let's start with this session. So until the last session, we have looked into decision trees, right? We have already looked into all the details into decision trees. Now what we are going to do is that we are going to start with some combination of the decision tree, which is otherwise known as ensemble methods. And one of the methods that we are going to try is the random forest. Now I'll go through what is ensemble methods as well first, and then we will look into what is a random forest. But I just want to clarify that random forest is not one of the ensemble methods which are there, but we will be talking only about random forest because usually what experience tells us is that overall for any such implementation where we have used decision trees, random forest almost always outperform a decision tree in terms of the accuracy. Now, when I say accuracy, I don't only mean the accuracy score which we will get out of a model. That is one of the parameters which we look into. We have already discussed this multiple times, right? That accuracy is not the only measure to guarantee that my model is good or my model is bad. There are many other things to be considered. Now, keeping all of those things in mind that we have already seen, like confusion matrix and precision and recall and so on and so forth, we will look into random forest, but we'll understand what is ensemble first. But the reason why we are specifically looking for random forest is because it is one of the methods, or it uses a method known as bagging, which we will understand. And because of that bagging method, it actually gives us more performance, uh, usually opposed to the decision tree, right? But there can be edge cases. There can be scenarios where this is not true. There can well be scenarios where this is not going to work. So let's first look into what is ensemble methods or what are known as ensembles. Okay, so as the word clearly suggests, if you look at the dictionary meaning of the word ensemble, you just search for ensemble. What does ensemble mean? It means together. So it is a French word. If you convert that into English, it means let's say together. So what we are going to do is in the ensemble methods, I can clearly say in case of ensemble methods, okay, we make we make multiple models of the same type to work together. Now this is not entirely correct, and that's why I'm going to mark that with a star. The reason why I'm marking this with a star is because there are also techniques, okay, there are also methods on to ensemble where okay where we don't only concentrate on one type, right? We don't only concentrate on one type. There are also ensemble methods like stacking where multiple types of models can be used or multiple types of models can come together, right? But in ensemble methods, what we usually do, we make multiple models of the same type to work together. That is the main point over here. So together word is actually to be marked into bold. That's why I'm marking it like this. So if you use a double star, right, then it comes into bold. But I have mentioned a star over here, which means that there are other cases. Let's say, however, there are other cases like stacking, where where we can actually mix together different types of models. Okay? What I mean by mixing different types of models is that in this case, in case of it's a random forest, what we are going to do, we are going to mix decision trees. So rather than creating one decision tree, I will be creating 10. Okay, by default, I will be creating 10 trees, right? And then I'm going to do something which is going to combine the power of those 10 trees, right? So rather than using one tree, now I will be using 10 trees, right? And I'm going to show you how this is going to improve the overall things or the overall performance of what we are trying to do, right? Now, ensemble is where we do uh, mixing or togetherness of things, and that is the reason why a random forest, we can say, a random forest is one of the ensemble methods where we will combine. Okay, I'm going to write this again into bold. We are going to combine multiple decision trees. So we are going to combine multiple decision trees and using techniques like bagging. Okay, bagging is actually a short form or kind of a miniaturized short form of something which is known as bootstrap aggregation, right? So we are also going to look into what is exactly bootstrap aggregation or how it works. But in case of a random forest, which is one of the ensemble methods, we are going to combine multiple decision trees, 10 by default, and using techniques like bagging, right? We will use this combination for our benefit, okay, for our benefit to get a better model. Okay. Now, when I say better model, it will not be only in terms of the accuracy. It can be basis other features or other factors also, right? But there are a few, however, I can say there are a few properties. Okay, there are a few properties of ensemble methods or the models which are in there. That is the models which comprise them, right? There are a few properties of the ensemble methods which should be maintained. Okay, I can say like this. So let's say there are a few properties that each and every item or each and every participant in that ensemble has to maintain. Okay, they have to maintain. There is no question about this. Okay, there cannot be any exception. The first thing is the most important thing is each and every element. So each model, okay, should be diverse, right? This means each one model is to complement the other one. If each model is doing the same thing, then there is no point of creating an ensemble. It's like doing the same work and expecting different output each time, right? Right. So what I'm going to do, let's say I'm peeling some vegetable here. So if I'm trying to peel a vegetable, and if I'm going to use the same kind of technique, the same kind of instrument to peel the vegetable, every time I use that same instrument, the outcome is going to be similar, right? There won't be much of a difference. If I use the same technique and same way to peel the same vegetable with the same tool, it's not going to make much of a difference, even if I do it for 100 times, right? So what I'm going to do, I'm going to change the way, I'm just going to change the way I use that tool. Okay. In this case of ensemble, we are not going to look into stacking where we are going to change the tool altogether itself. In case of stacking, what happens is you change the tool itself. Okay, you make a change in the tool. Now I'm not going to change the tool, I'm not going to change the instrument which I'm going to use to peel that specific uh, item, right? Instead, what I'm going to do, I'm going to change the way I'm using the tool, and that change in way is going to complement each other, right? This also means that the predictions, okay, given by each model is independent, okay, is independent of one another, right? So if they are complementary to one another, obviously the predictions which is given by one is not going to be affected by the predictions which is given by another. However, keeping this in mind, we also have to ensure that each model is acceptable, right? Which means it means each of the model, each one model, I'll say each one model is at least better than any random model or any other randomly chosen model, right? So for example, if I'm going to bag 10 decision trees and I'm going to create one random forest model using 10 or 20 decision trees, each and every of these decision trees has to be created in a way, or their combination has to be unique. Their combination has to be better than, let's say, any other classification model, let's say like a logistic regression, right? But if they are not performing as well as a logistic regression, then ultimately I've not done anything well, right? Even if I do a lot of tips and tricks, it's not going to help, right? Now, what we are going to do to understand this problem, we will go back to Excel. Okay, we will go back to Excel and then we will find out what is really happening in this case. Okay, so in supplementary, I'll just write it over here. In supplementary Excel sheet, we will understand the basic concept. Okay, the basic underlying concept of an ensemble. Okay, and then later we are going to talk about the bagging techniques. Okay, let me just open an Excel sheet. Let me open an Excel sheet and let me share it. I know you might be having some questions, most probably by now, but once we are done, okay, once we are done with the explanation, I'm sure a lot of questions will get solved. And then we can look into more questions. I've just opened an Excel sheet. Let me just share that with all of you. So this is what I'm sharing now. I hope you can see it now. So what I'm going to do, I would like to, let's say, okay, I would like to, let's say, create only 3 models just for the brevity or just for the sake of, let's say, simplicity. Okay, I'm going to take 10 cases. Okay, 1, 2, 3, 4, 5, and I'm just going to drag and drop over these. So I'm going to take 10 cases. I will tell you what these 10 cases actually mean. And I'm going to take the outcomes of 3 models, let's say M1, M2, and M3. Okay, so let's say I have uh, decision tree models, right? I have three decision tree models, and here I'm going to write the result. Okay, you will come to know what is this result actually meaning. Okay, and then also going to write, let's say, a probability factor, right? I'm also going to write a probability factor. I'm just going to do a margin center on these cells so that it looks nice. And then I'm also going to do a margin center on these 3 cells, and I'm going to say this is the result, the result of each model. Okay, so what I'm doing, let's say, for the same kind of a data set, for the same data that I have in hand, for the same use case, okay, what I'm doing, I am going to train my model 10 times. So I have 3 models, I'm going to train them 10 times, which means I will have 30 total fits for each and every fit. Okay, for each and every fit, okay, it is going to give me some outcome, right? It is going to give me some outcome for any particular, okay, for any particular data point. Okay, so these results, okay, that I'm actually getting can be, okay, this case can be considered that these are 10 runs for one single row. So I will just write it over here just for the clarity. The number of cases can be 10 different fits or runs of 3 models we chose on a single test data. Okay, so let's say we have already trained our model. Okay, we have already trained our model and we are testing our model. Okay, and we have only one row where we are testing our model. Or it may well be the fact it can also be considered, or it may well be the fact that we have 3 models already trained which are being tested on 10 data points, and hence each data point refers to one case individually. I hope you got my point. So my point is that these 10 cases are either 10 data points, each on which I'm trying to predict the outcome. Okay, the outcome using 3 models that I have trained. Okay, or it can be only one test row only, right? Only one observation in my test data where I'm running these models for 10 times with 10 different types and kinds of etc. hyperparameters, right? Now what this results into is, let's say I have a binary classification problem. Just to simplify, okay, just to simplify, let's say imagine we have a binary classification issue, okay, where the outcome, okay, the outcome is either of correct and incorrect, right? So I can have only two outcomes. I can have only two outcomes. Okay, the outcome can either be correct, which you can label as one, right, or you can label the outcome as incorrect, or otherwise let's say zero, right? Okay, now each and every model, right, each and every model, let's say, has an accuracy percentage, okay, has an accuracy percentage of 0.7. Okay, each and every model has an accuracy. I'm just going to simplify my use case so that I can better understand it. So let's say each and every model has an accuracy score of, let's say, 70%. And let's say I have a very balanced kind of a data. I don't have class imbalance, right? I have good amount of, or let's say good amount of data, good amount of sample I have, and I have really good balance between the positive and the negative classes, right? Now, for each and every class predicting correctly, they are 70% correct. So the accuracy score is, let's say, 0.7. Now, for the first case, let's say it is correct. I'm going to mention correct as C and incorrect as I. Okay. So let's say for the first observation, for the first case, all of them are C, right? The result is going to be what? If all of them are correct, the result of the ensemble is also correct. Why? Because ensemble means these three have to work in the same way. So they all have to be considered together, which means if all are saying yes, right? If all are saying yes, then my final result is yes, right? This is what we are trying to figure out. So what we are saying over here is the basic rule of ensemble here is a method that I'm using over here, or the basic method, let's say, I can write it over here. The basic method used over here across across my three models is voting, right? So, for example, if some IPL match is going on, or if some political parties are actually rallying into a race in a state, and we three, right, we three are there in this call. So, if we three are saying that political party A is going to win, right, my ensemble, my final outcome is going to be that political party A is going to win. This is what our combined vote is. So we all believe, truly believe, that political party A is going to win, right? If majority says no, if majority says no, then we are going to say otherwise. So let's say in the next case, I'm just going to flip around things. Two are saying they are correct outputs, and one is predicting incorrect. In this case, also that is the case. Let's say this is CIC, and then this is I, B, and C, right? In this case also, in this cases, the results will be C only, right? The final outcome of the ensemble will be correct only, right? The final ensemble is going to be correct only. Why? Because majority are saying correct. You see, two out of three models have predicted for observation number four, for observation number four or case number four. One is saying the outcome belongs to class incorrect, but two are saying it belongs to class correct. Hence, the final outcome is going to be correct, right? Now, what I'm going to do, I'm just going to mix and match this. Yeah, I'm just going to mix and match this, and then we are going to look into final thing. So let's say, in this case, let's say for the fifth case, this is going to be I, C. In this case, because the majority is incorrect, I'm going to say this is incorrect, right? Okay. I'm going to say this is incorrect. Maybe even a better thing will be, let me just delete these two rows. This will make my life easy actually. It will make my example easy. So I'm going to say I, P, I, and then C, I, I, right? And then I, right? So in this case, what I'm getting? I, I and I, right? So for this observation, it will be I. For this observation, obviously, it will be I. Now let's try to calculate the probability. The combined probability is going to be what these three are happening at the same time. These are not exclusive events, right? Basics of probability says if three things or n number of things are happening at once, the total probability becomes the multiplication, right? If they were independent events, I would have summed them. But these are independent, but they are happening at the same time, right? They are independent event, but they are happening at the same time. So that's the reason why if correctness accuracy of the model, if the model accuracy is 0.7 and all of them are saying C and C, then my outcome is going to be 0.7 multiplied by 0.7 multiplied by 0, right? In the second case, it will be what? 0.7 multiplied by 0.7 multiplied by 0.3. Right? I think I have done some mistake over here. I have not given the equal to sign. That's the reason why it is not calculating. In the second cell also, I have made a mistake. Let me just correct that mistake. So multiplied by 0.3, right? Now, this value is going to be the same for the next two cells. So I'm just going to copy paste it there because I have one incorrect. So probability is getting calculated not by looking at the result. I'm not looking at the result. I'm looking at the accuracy values and I'm trying to multiply them for these observations, the actual outcomes. Then in this case, what is going to happen? 0.3 multiplied by 0.3 multiplied by 0.7. Right? If this is the case, I can simply copy paste this over here, and over here. And for the last case, I'm going to say is equal to 0.3 multiplied by 0.3 multiplied by 0.3. Right? So this is the final thing. Give me 1 minute, friends. I just realized that my battery is draining. Let me just put the charge in. Now, if I look into this, okay, if I clearly look into this, okay, in this table, there are four cases where each decision of the final model is either correct or incorrect, right? Either it is correct or incorrect. Let us, okay. Now, if I say, let's say, if if okay, P is the probability, okay, P is the probability of of the final outcome, or the ensemble, ensemble being correct, right? And Q being incorrect, right? Then I can say what? I can say P, okay, P is equal to the summation of the first four cells. Okay? The summation of the first four cells. So I can take the sum first and then I'm going to put it over here. So I'm just going to say sum, the summation of the first four cells is going to be this is equal to 0.784, right? And Q is going to become the summation of, or it will be 1 minus P, right? So 1 minus P is going to be what? Approximately 0.216, right? 0.216. It is how it is going to be. So let me just do this. Yeah. So this is what it is. This is how it is going to look like. So for my, let me just move this. So for my ensemble to be correct, or for my ensemble to be giving me the correct outcome, okay, to be giving me the correct outcome, okay, I am getting a probability of 0.784, right? If I combine three models, you see that the probability, or the accuracy of my model, okay, or the chances of getting correct answer is actually now 0.784, right? And the chances of getting an incorrect answer is 0.216. The more I increase the number of models, obviously this is going to increase, right? So clearly I can see that earlier my individual model's accuracy was equal to 0.7. Now I have a model accuracy, combined model accuracy of 0.784, right? So from 70% to 78.4%, I have jumped. only because of the fact that I have combined the power of three modules and I have taken a vote. I took a vote, I took a probabilistic vote, and now I am able to actually get three modules which are better than only creating one module, right? Until this point in time, friends, do you have any doubts? Because this is the basic thing which we are going to do throughout. If you have any doubt, please let me know. Any questions? Okay, I'll assume that you have no questions, right? Then, if this is the case, this is exactly what we are going to do in the random forest, because random forest is a type of uh, ensemble, right? The random forest is a type of ensemble, but then what I'm going to also say is that I can also say, I'll get back to my notebook, and here I can also say, in reality, okay, in reality, and this will increase the complexity for some time, but later when we understand what exactly is happening in bootstrap aggregation, we will know what is the case over here. In reality, okay, random forest, I'm just going to write them as RF, are created using a special special ensemble method known as bagging, right? Bagging stands for bootstrap aggregation, right? Which stands for bootstrap aggregation. Now, what is bootstrap aggregation? Let's try to break these two words and we will come to know, right? So the first word is bootstrap, right? And the second word is what? Aggregation. Aggregation, right? Bootstrap in this context, okay, simply means okay, okay, creating valuable or bootstrap samples, okay, from a given data set which do not overlap, right? So this is similar to the concept of k-fold. Okay, similar to the concept of k-fold, not exactly similar, similar to the concept of k-fold. Similar to the concept of k-fold, we can do bootstrap sampling. I'm going to show you a picture, and that picture is going to clear the doubts. Now, aggregation means what? Means combining the results. Simply, right? Aggregation means what? If you have worked on to SQL, or if you have worked on to any kind of aggregation functions like sum, right? If in that Excel only, right? I did a sum of 4 cells, then I did a sum of another 4 cells. I did an aggregation. I simply combined all the values using some function. So aggregation is the same thing here. In this context also, aggregation means the same thing. Bootstrap is just a statistical word. And that word comes from the fact that I'm creating a bootstrap sample now. You might be wondering what is a bootstrap sample. So I'll clearly write it over here. Okay, I'll clearly write it over here. Point number 6. Bootstrap sample. The bootstrap sample in the statistics world, okay, is created by sampling given a data set, okay, uniformly and with replacements, right? It is done uniformly and with replacement. Give me 1 minute. Okay, I'll actually take this call at a later stage. Fine. So bootstrap sample is created by sampling a given data set uniformly and with replacement, right? The bootstrap sample typically contains about 70-30 of the data. Okay, the usual rule, okay, of bootstrapping is 70 cross 50. Okay, so let's look at some images. I'm going to do image search, and in the image, I'm going to say bootstrap sampling. Okay, if I just search for bootstrap sampling, this is what is happening. This is one good image. This is also one good image. I'll show you both. Let me just open this link in new tab and open the image in new tab, and I'll close this. This is one image, but this is a very small image. I hope you can see the colors, right? So what I am doing over here is, Okay, I have a sample of 5 items here. Okay, I have a sample of 5 items over here. 1, 2, 3, 4, and 5. And I have bootstrapped it. Okay? What I am doing over here is, rather than taking one item always once, I'm taking one item twice. This is one way to bootstrap, right? This is one way in which usually I mix and match things so that I can maintain the variety as well as not maintain the variety. Now, one more way of doing bootstrapping is this. Open image in new tab if I do. This is one very cool way of doing bootstrap aggregation, which is used in any kind of ensemble classifiers that we are going to use. So, for example, in case of, let's say, random forest, if I have an original data set like this, I take, you see what I'm doing over here. I'm majorly taking on this side. Let me take the pen. Okay, so I have all the samples over here. I have the original data. This is the original data. Okay. Now what I'm doing from the original data, I'm using one bootstrap sample. This is sample number one. In sample number one, majority are orange. Okay, these are, I think, no, these are the yellows. Okay, so majority ones are the yellows, but then there are mixing. Okay, there are mixing of other colors also, like the violet ones, the orange ones, the blue ones, and so on. Ideally, what I should have done is I should have taken, or in ideal case, I should have either done a random sampling where there was an equal chance for everyone to fall into each and every sample. But in this case, I'm doing is in each and every sample, I'm bootstrapping them in such a way that one kind, okay, in this case the yellow kind, okay, one such kind or one kind of data is getting a preference, while the rest are getting the rest of the preference. So 60% of the data, you see 1, 2, 3, 4, 5, okay, 50% of the data in my sample S1 is actually yellow. Okay, and the rest 50% are one or two types of the rest, right? In the same way, I'm doing over here. In the same way, I'm doing in the next sample. In the same way, I'm doing in the next sample. And in this way, I'm creating n number of samples. Okay? N number of samples. Right? The only difference, the only thing which cannot be showed in this picture because they have not really numbered it in a good way, is that I can do, okay, in case of bootstrap sampling, I can do with replacement sampling also. So in case of bootstrap sampling, ideal bootstrap sampling, what we do with replacement things. Right? So there is an equal probability. Let's say this blue over here can well be this blue, right? So it is like with replacement. It's like you imagine you have a bag of balls and you are picking up 3 balls. One is red, one is black, and one is blue, right? And you put those 3 balls back again. Then let's say someone else is picking up the ball, right? And then someone else is picking up 3 balls. Okay, there are many blue balls in that bag, but there is a very good chance. There is a likely chance that I will get that same blue ball which you have picked. Okay, that is known as replacement. So I am replacing a ball. I'm putting the ball back and picking up one more. So there is a chance of the same sample getting selected again also. Okay, but it is okay. It is okay because I will, to avoid the effect or avoid the anti-effect of the same data set getting selected multiple times, I'm going to select a lot of samples, right? Then the probability of the same ball getting selected multiple times is going to diminish, right? And that is the reason why usually what we do in the ensemble cases, we don't create 10 models. Usually we create, let's say, 20 models. Usually we're going to create, let's say, 30 models. And then we are going to, after we have bootstrapped and after we have performed the classification. So for each and every sample, we perform the classification. And then we aggregate the results using the simple methodology that I have shown you. There are other algorithms also. I've just shown you one of the methodologies. The one that I showed you in the Accelerate, that is one of the methodology. This is not the methodology. It is just one of the methodologies in which the results are combined with each other. Once they are combined with each other, the entire process is known as bagging. And now I have a random forest model, or now I have an ensemble model, which is actually a combination of more than one model, or let's say more than 20 models, right? So the power, yeah, the power of the models are going to improve, right? That's exactly what we are doing over here. Let me just clear the drawings. Let me close these. Okay. Now what we are going to do? Now what we are going to do is that uh, maybe I can write the steps also. Okay, let me write the steps. Let me write the steps. Let me, just for your reference, let me write the steps before we go on to the practical coding part, right? Let's write the steps. So let's say what exactly happens in any random forest classifier implementation is as follows, or it can be summarized as follows. I'm just using my own words, so it might be different in different textbooks. First of all, what I'm going to do, I have the training data. I have to create the model on the training data. I will be validating it on the testing data, right? So I'm creating the model on my training data. Hence, I'll create a bootstrap sample from the training set, right? I'm going to create a bootstrap sample from my training set. So randomly, I'm going to select some rows, right? Now, construct a decision tree. Okay, because I am using a random forest is going to be collection of the decision tree. It is quite synonymous to the name also. In a forest, we have a lot of trees. Right? A forest is not going to have a single tree. So that is from where the name comes, maybe. Now, we are going to construct a decision tree using the bootstrap samples, right? Using the bootstrap sample. The only thing we have to take care of is while splitting the node of the tree, okay, we will only consider a random subset of features, okay, every time. So this means that is every time a node has to be split, okay, a different random subset of features will be considered, right? And this is the second stage. Now what I'm going to do, I'm simply going to repeat the steps one and two above, one and two above. Okay, because I've not really numbered them, they are numbered by hashes, so you have to read it like them. So this is step number one, this is step number two. So maybe I'll write them over here. Step number one, this will be step number two. This is going to be step number three. Okay, step number three is repeat steps one and two above. Okay, for n number of times. Okay, for n number of times, right? I'm going to repeat the above steps. Uh, Creating, or this results into creating, okay, n trees, right? If I do the above exercises for n number of times, I'm going to result in creating n number of trees, right? So since each tree is independent of each other, as I've already mentioned, right? Each and every tree has to be independent of each other. Okay, that is the property. They are independent of one another. Because they are independent of one another, they can be created in parallel because they have no relationship or no dependency with one another, right? So I can create one tree, you can create one tree, Sarangs can create one tree, and so on and so forth, right? So one can be created by me, one can be created by Rohi, and so on, right? Or maybe we, each and every one of us, are going to create three trees, and they can be created, let's say, parallelly also, right? So there is no dependency, there is no inter correlation, or let's say there will be no effect of one tree on another, right? Now, the final step, while predicting a test case. So I have the testing data also. While predicting the outcome of any test observation, each tree, okay, predicts individually, and the final prediction is given by what? Is given by the majority vote, right? The majority vote of all the trees, right? This is exactly what happens in a decision tree. Now, there are a few advantages. Obviously, we can see there are a few advantages of using the random forest. It is usually more stable. Okay, I'm not saying it is more stable in all the cases. I have myself seen, okay, I have myself seen a case into Kaggle when I was working with one of the data sets where not using decision tree or not using random forest actually gave me a better result because I used a logistic regression model, right? I used a logistic regression model, then I used a decision tree model, then I used a random forest model. The decision tree and the random forest were not that good as opposed to the logistic regression model. I was actually able to do better with the logistic regression model. So there is a very good probability that even a single, let's say, decision tree, it can happen. Okay, it can happen that a single, let's say, decision tree or any other kind of a model which is not using ensemble or any bagging or any such kind of bootstrapping kind of techniques, they can actually work better. Okay, it actually depends on the use case which you have. So let's say if my data is really clearly separable, right? They are linearly separable also. In many of the cases, logistic regression will give me very good output. So I don't even need to consider as a decision tree. Right? But it is usually more stable than single decision trees. So I can say this, that it is usually more stable than single decision trees, since it is not affected by the instability of any one of the trees. Okay, so for example, let's say because of some valid reason we still have outliers in our data, and having outliers in our data is really going to affect a model, right? But if I'm going to create, let's say, 20 models, that effect of having a valid outlier can be diminished, right? The effect of having a very valid outlier can be diminished. Even if one of the decision trees that I've created has some kind of a problem because of a wrong observation which I may have overlooked, I may have not done data wrangling to such a depth that each and every row was cross-checked, right? Let's say I have a data set which is like it's a 60 GB in size or 100 GB in size. It is not really humanly possible for you to check each and every details of each and every column. Maybe you have missed it, right? In that case also, that effect will not come into place, right? The effect is not going to come into your final output. That kind of stability is there. That kind of stability is there, right? Now, the second most important point is usually, right? Usually it is immune, okay, to the curse of dimensionality. This is one very, very important point. Why I am saying this is because if you look at step number two, every time a node is split, a different random subset of features are considered. Every time a node is split, a different random subset of features are considered, which means I don't really have to bother about dimensionality reduction unless and until I have humongous amount of, let's say I have humongous amount of features. Let's say if I have a feature list of, let's say, 500 features or 600 features, maybe at that point in time I have to really think about PCA. You have not learned about PCA or LDA or the MNI or the TSNE. These comes under unsupervised learning. We said that we'll complete supervised first and then we'll go there. So we will look into dimensionality reduction. They really help. Okay, they are really, really going to help. But in case of random forest, if we really have higher, let's say, columns, higher number of features, let's say 30, 40, or even 50, even that effect of the curse of dimensionality can be reduced, because you already know the more dimensions we add, the more problems we are adding of choosing the right columns using VIF and RFE. If we do any single mistake, right, then the effects are going to be drastic, right? If it is left out, the effects are going to be drastic, right? So that is already taken care of because of that point that I've explained. Step number two over there, right? Also, the third good thing, this is from a computer engineer perspective, you can say, uh, right? Can parallelize. We can parallelize. Okay, we can parallelize the training of forest, since each tree is constructed, I'll say constructed independently, right? Because each of the trees are constructed independently. Sorry, what did I do? Why is it doing like this? I'm not sure. Let me just see what it is doing. There is some issue. Okay, let me see if I can really fix that at a later stage. But there is some problem, friends. Here, this should not be the case. So let me just see if I just remove this. Maybe this will work. But then the point of putting that point is gone, right? I mean, this should not happen, but it's okay. Let's try to just find out a way. Right. Let's see if this works. Yes, this will work, but it does not really look good, right? But it's okay. I believe we have got the initial set of nodes, right? Now, as of now, this is all we need to know, right? As of now, this is all we need to know. There is one issue, right? There is one issue. There is also one issue, and I'm going to mention it over here, but I'm not going to explain that right now. So disadvantages, OOB error. I'm not going to explain this. I'm just going to tell you the full form. Out of bag errors, right? This is a very, very common issue with random forest, or for that matter, any ensemble case. Out of bag error is a very, very uh, observable problem with any of the ensemble methods. Let's not explain that right now. It is only going to confuse you. When we create the model, then we are going to look at it. Right now, the time taken to create a model is going to depend on how or in what way you are going to sample your data and so on and so forth. Right. So let's just start with the analysis. I have some data of credit card default. I'll just show you what is happening over here. So these are a few columns which I have over here, right? These are a few columns that I have over here. So this data that we have over here, okay, is where I have some columns related to the credit card defaults that my users have made. Okay, so the target outcome is the defaulted field. So this can have a value of 1 or 0. Okay, then I have some ID field. This will not be required. We will obviously be dropping it. Then there will be some attributes of the customers first, right? And then there is going to be some of the bill amounts which they have paid against some of the actual bill amounts, right? And the pay amounts and so on, and then whether they have defaulted or not. So we have some columns of data over here, by means of which we are going to find out whether my customer is going to default or not. So what I'm going to do, I'm simply going to take this data. I'm going to take this data. I'm not going to, or I may not really spend much time onto uh, creating the EDA and so on, just to save time. We will go directly into the modeling part, right? We will try to select the features. We'll go into the modeling part, and then we'll see what advantages we get with the random forest, right? So let's say import pandas as PD. Okay, give me 1 minute. 1 minute. Do this. Yes. Import pandas as PD. Then what library do I need? Let's import NumPy also as NP. Okay, then I'm going to, let's say, import matplotlib PI as PLT. Okay, then I'm going to, let's say, import cbond as SNS. Then let's say I'm going to say matplotlib inline, so that it prints all the charts inline. Usually Jupyter Notebook does that, but just for the sake of brevity, I'm doing this because in some cases I've seen it does not do. Then also I'm going to do import warnings, and I'm going to say warnings dot filter warnings. I'm going to ignore. Okay? I'm going to ignore them. Right? I'm going to ignore them. Now what I'm going to do, I'm simply going to create a data frame which is going to read my file, read underscore CSV, and then I put the name of my file that I have copied. Let me see. Pf.head. Am I able to read that? Yes. So I have a lot of columns over here. What I'm going to do first of all is that I'm not going to look much into the data, as I said, right? I'm not going to look much into the data. What I'm going to do, I'm just going to look into the information. Okay, let's see what kind of information it has. Looks like a very well prepared kind of a data, might well be a dummy data also, because or otherwise the master data management is really very good from wherever this data is really uh, captured, because there is no null row. You see, there are 30,000 entries, and all of them are really prepared very well. They are all the numeric fields. This is a very, very rare case, right? And we really have some very good amount of data. Now, obviously, I can do a pair plotting and I can try to find out the relationship, but that's only going to take some time. Okay, so what I'm going to do, I'm going to simply jump onto, okay, I'm going to simply jump onto my um, implementation stage. Okay, I'm just going to jump onto my implementation stage. Okay, even what I can do is that a df dot drop, I should really not care about that ID column. So I'm just going to drop it. I'm going to say access is equal to 1 and in place is equal to 2. Okay, now I have the rest of the column. So I don't have that ID column because I really do not need that. All right. Now let's do one thing. From sklearn dot tree tree imported decision tree. Okay, I'm just going to import the decision tree. Okay, sorry, decision tree classifier it will be. Okay. Then I'm going to from sklearn dot model selection import pen test split. Right. Now I'm going to create x and y. X and y is going to be, let's say, in this case, what is going to be my x? X is going to be anything other than defaulted. So I'm going to say df dot drop and my target column is defaulted and I say axis is equal to 1. I don't say in place is equal to true. If I say in place equal to true, it goes away from the data frame. So I'm creating a new data frame x by dropping the defaulted column as a result from df, right? So I get x as this, or I can also do x dot info and I can get the details of the columns. I have all the features, and now y is going to be df and it will be defaulted. Right? Y is going to be defaulted. So y dot head, I'm going to get the values like this. Right? Now what I'm going to do, I'm going to create a simple, let's say, decision tree classifier. Okay. dt is equal to decision tree classifier and I'm just going to fit my model. And to fit my model, I have to create the training and the testing set. Extend x test y train y test is equal to train test split. I'm going to use x and y. I'm going to give it a test size of, let's say, 0 0.3. Sorry, it should be 0 0.3. And I'm going to give it a random state of, let's say, 101. Right? Now I have the training data and the testing data. Let me just fit my model quickly on the training data, x train and y train. So my model is there, right? Now I'm going to create a y pred dt, which is equal to dt dot predict x test, right? Now from sklearn dot metrics import accuracy score and confusion matrix, right? And I'm going to say print confusion matrix and pass it y pred dt comma y test. And this is the confusion matrix. Out of the box, it is not really very bad if you look at it. It's what 2,400 rows approximately, or 2,500 rows. Okay, 2,500 rows are estimated badly, and the rest, how much? 6,400 rows are estimated really correctly. So it is not a very bad model. And if I look at what is going to be the accuracy score, let's say, I'm going to look at the accuracy score, y pred dt and y test, then I get an accuracy of 72.15. But is accuracy the right thing to look at? Let's look at this df dot defaulted dot value uh, counts. I do a value counts. It's an improperly balanced thing. Okay, it is an improperly balanced data. So confusion matrix is going to be a better thing to look into rather than the accuracy score, right? But now what I'm going to do from sklearn dot ensemble, okay, import random forest classifier. Okay, I'm not doing anything other than simply importing the modules. I'm not doing anything other than importing the by default modules which I have. Later on, I'm going to improve them. Later on, I'm going to do grid search CV and all those things to improve my model. As of now, I'm simply importing the model. I will simply import the model. I'll see what is the out of box thing which I get. So RFC is the random forest classifier. I'm just creating an object over there. And then RFC dot fit extend y train, right? Now what I'm going to say y pred RFC is going to be see how much time it is actually taking to fit, because it actually depends on how good my laptop is, right? So I just have a mediocre kind of a laptop, so it took some time. It took actually good amount of time as compared to the decision tree that I fit. But I'm going to get the predictions now. So I'm going to say rfc.predict x test, right? And now I'm going to say print confusion matrix and use y pred rfc against y test. Okay. Now you look at the answer. If you compare the first confusion matrix with the second one, you have a very, very good kind of a model out of box. You don't have to do much. You see, if you look at the accuracy score also, although we really should not be looking at this because we have class imbalance, so accuracy score is not going to be the right thing to look at. But without doing anything, a decision tree gave me a 72% accuracy, and a random forest gave me an 82% accuracy, right? This is almost always the case. I'm not saying this is always going to be the case. Okay, this will not always be the case. Almost always. As I told you, one example, I don't remember the data set. If I remember, I'll also share that with you. In that specific data set, right? Logistic regression gave me a better thing. Okay, logistic regression gave me a better thing. Okay, now there is one more thing. I believe there was a classification report. I did not import that from sklearn.metrics. Import classification report. This is really cool. I'll show you why. If I do a print of classification report, because I'm not relying on the accuracy score here, there's a class imbalance, so I'm not going to rely on that. So I'm just going to look at the decision tree one. Okay, you see what is happening over here. For one class, the precision and recall is very good. For the other class, it is comparable, but the value is low, right? I mean, it's not a bad model. If you look at this, precision and recall for one class is close to one another. Precision and recall for the other class is close to one another. But if you look at the comparative value, one is it, the precision and recall of class one is actually half of that of zero. So what happens? I simply take this and I come over here and I paste it here. And instead of DT, let me use RFC. Right? You see what is happening here. There is a strange thing which you see over here. Precision and recall are now different. They are spreading out, right? The precision and recall are actually spreading out. Okay. But in this case, I will tell you what is the advantage of using a random forest is that you have a better F1 score. And what is an F1 score? Let's quickly look at it. I believe I did explain this to you, but let me just quickly tell you what is a F1 score. F1 score actually penalizes the effect of precision and recall on the classification. Okay, or from the classification. So from the classification, whenever we are getting precision and recall, if there are many models which we are stacking, or if there are many properties of the models that we are changing or we are altering to get a better model, this is where F1 score actually comes handy, as opposed to using the accuracy measure or as opposed to using anything else. Right? So F1 score, if you look at it, classification accuracy is not enough. You can read about this also. Okay, so I'll share this link with you. This is a very, very good thing. I read it once. This website is really very good. I'll share this with you quickly. Okay, and F1 score is really a very good kind of a metric. I look at it always. But if you look at the F1 score now, you will see that the F1 score of the previous model is lesser than the one which is in this model. So I have a better F1 score. So a combination of precision and recall. If you look at the formula, it's like a combination. So the combination of precision and recall is actually better for my random forest classifier model as opposed to a decision tree model. Now, this is not to say that my random forest classifier is really the best model. We have not looked into what is the disadvantage, right? The disadvantage is out of bag classification errors. It will happen. It is still there in this model also. It is there. It is there. I mean, by default, that disadvantage is there in each and every random forest classifier which we create, but we don't know what that is. So we will read about it in the next session, right? So tomorrow when we meet, we are going to read about it. We are going to understand what is this out of bag classification error and thing, right? And then we are going to go in depth, right? But as of now, this is what we wanted to cover. Just as a start, we created a single decision tree. We looked at the performance. We created multiple decision trees. Now the point is how many decision trees it we create over here. Let's just quickly look into this. sklearn dot ensemble random forest classifier. So if I look at random forest classifier, let me see what is the default value. There is a parameter, there is a hyper parameter which is n estimators. In this version 0.23.2, n estimators default value is equal to 100. Okay, so the number of trees in the forest, right? Number of trees in the forest is 100. Now, what this is saying changed in version 0.22. Default value of n estimators changed from 10 to 100 in version 0.22. I believe this is the one that I am using. Let me just quickly see. Pip so scikit learn. I believe this is the command or it should be. So yes, so I'm using 23.1, right? So it is quite closer to 23.2. The default I have built 100 decision trees with the criterion, the way to identify the error or the impurity is actually Guinea. Max depth we have not selected. Mean sample split is 2. Okay, mean sample leaf is 1. Okay, these are the hyperparameters which we have to tune. Okay, these are the hyperparameters that we have to tune. Here you see there is a hyperparameter called max features. Number of features to consider when looking at the best split. I told you, right? You look at point number B over here. In point number B, I told you what? Step number 2, every time a node is split, a different random subset of features will be considered. You can control the way it is considered also. It can be auto, by default it is auto, or you can do a square root kind of an operation here also on the number of features, and you can randomly select the features from there. You can do a logarithm also and so on, right? But with the default random forest, which has fit 100 trees, I've actually got a better model over here. Rather than creating one tree, I fit 100 trees, right? And the aggregation has provided a better outcome because I have bootstrapped the sample. I have mixed and matched the samples of the data, right? That is the advantage of using an ensemble technique. Let me just share this link with you also. And most probably, if we don't have any questions here, friends, then we can close the session also. Do we have any questions, friends?
No questions from me. Actually, I have a simple question.
Yeah.
Uh, so when we say two techniques, one is regression technique and second is classification, and the third thing is classification and regression technique.
Yes.
Okay, so Bhaumik, what's the main difference between the classification and the classification and regression technique?
Okay. So basically, what you will see over here is that if I simply run this, okay, random forest regressor. Okay, so rather than searching for random forest classifier, now I'm going to search for sklearn ensemble random forest regressor. Okay. And I will go to a documentation which is for the random forest regressor. So what is happening over here is the
Mm-hmm.
same, okay, the same methodology, okay, with the same kind of parameters, a few hyper parameters might change. The same algorithms and the same way to do things or to create the model is getting used for both. It is getting used to do the classification as well as the regression. So there can well be techniques, let's say example given like the random forest technique, or for that matter, there are techniques which are the usually the ensemble ones, which are used for doing both the classification as well as the regression, right? But there are a few techniques which are by default used either to do classification or to do regression, right? So this is the basic difference between what CART techniques are going to mean. So these will be techniques which are created in such a way that they are applicable equivocally, both on the classification problem as well as a regression problem, with some tweaks. Did that answer your
Yeah,
question or did I confuse
yeah,
you?
Bhaumik, got it, got it.
There is actually more to that also, but in a simple word, this is what it is. So with respect to the functionality, they do both. So they are created in a way that they can use, They can be used as a classifier as well as a regressor. Any other questions, friends? Any question from you, Rohit?
No questions as of now.
Okay. Okay, friends. Then let's close the session as of now. So tomorrow we will meet at the same time. Then we are going to continue. We will see what is that out of bag error, and then we have to use grid search, cross validation, and so on to improve the stability of our model. Right? Okay, friends. Thank you for joining. Good night.
Thanks,
Thanks,
Bobby.
Mamik. Good night.
Thank you. Thank you.